This is PreCalculus A, Unit 2, Lesson 1, Domain and Range of a Function. So we'll introduce some of the concepts here. For a detailed explanation, of course, refer to your lesson materials. So feel free to take some notes as you go. Basically, the idea of this is that domain is all the x's. Domain, all the x's. All the x's, it's also called the input. Okay, whereas range is all the y's, or all the output. Okay, and we need to introduce something called, there's two different kinds of notation for domain and range. One is called set builder, and another is called interval. Okay, and so this is some notation, mathematical notation. For example, we might say we have the set of all numbers such that x, all numbers x, such that x is greater than 2. Okay, so that would be represented graphically as 2 on the number line, open circle, shade to the right, where 3 is here, 4, 5, 1, 0, -1, and so on. Okay, hopefully this is a review from material that you've learned in Algebra 1 and Algebra 2 as well. Okay, maybe with the exception of the braces and the notation x such that. This is such that. X such that. All x such that. And then we provide some condition. That's set builder notation. We introduce another type of notation, that's interval notation. Okay, and we would write this in interval notation as parentheses 2, comma, infinity, close parentheses. Okay, and that represents the same thing, the set of all numbers greater than 2, not equivalent to 2. Okay, well, this is called an open boundary. An open boundary. And by the way, we always, if one of the boundaries is infinity, that is always open. Because infinity is a quantity that you never reach. It's an unbounded boundary. So it's a non-boundary boundary, so to speak. Right? Because you never actually reach infinity. All right? What if I change this notation to read all x such that x is greater than or equal to 3, and it is less than 5. Okay, we would say x is between 3 and 5. So here's 3, here's 4, here's 5. So we would close or shade in the 3. We would not shade in the 5, and we would graph the numbers between, right? So that's a closed boundary, and this is an open boundary. It's called an open boundary because there is no absolute greatest number. We might say, well, maybe the greatest number is 4.9. No, 4.99 is greater than that. Well, maybe the greatest number is 4.99. No, 4.999 is greater than that. No matter what number less than 5 you write, you can always find one bigger than that that's still less than 5. So it's called an open boundary. It's a soft boundary, so to speak, as opposed to a hard boundary, where there's a specific number that serves as the ultimate end. Okay? Interval notation uses a square bracket for the 3 and the parentheses for the 5. Okay, so this is a closed boundary. Okay, it's an absolute limit of 3. 3 is the lower limit. Whereas this is an open boundary. 5 is a soft boundary. In other words, we don't include 5, but simply we include all numbers less than 5. Right? And there's no absolute maximum in this case. All right. Some other notation here. If we want to combine units, so we might say in set builder, x such that x is less than 3, or x is greater than or equal to 5. Okay. And so the graph of that would look something like this. If this is 3 and this is 5. Less than 3 would be an open circle at 3 with an arrow pointing to the left. Greater than or equal to 5, we fill in the circle, shade to the right. right? So that would be set builder notation, whereas interval notation would look like this. It would go from negative infinity to 3 with a soft boundary. Union, that's how we combine sets. Union. That's not a U, it is actually a set notation symbol meaning union, as opposed to intersection, which would be the shared parts of two sets. This is combining two sets absolutely. All right, and then closed interval 5, open interval infinity. Okay, so that's the notation, and we come across it when we want to write the domain and range of various functions here. Let's give an example in a graph here of a function. So let's say we've got something behaving asymptotically here, and then goes up to here, has a closed interval or open interval, then goes down to here, behaves like a line, right? And then another closed interval, and then like so. Let's see. And let's say it acts asymptotically here and never crosses this line. Okay, and behaves like this with a hole right here, right? And then actually let's put the hole right here. Okay, this is a complex one here. Okay, so I would say the domain, if I need to superimpose a number line on this here. Okay, here we go. The domain would be from, we don't have numbers. Got to have numbers. Okay, let's say 0 is right here. 1, 2, 3, 4, 5, negative 5. 1, 2, 3, 4, so 4, and then 6. Okay, so the domain of this, which would be all the possible x values, would be domain. The main the domain would be negative infinity, because that goes off to negative infinity, to 5, right? But there's a hard boundary there, right? Or a hard boundary on the other one, and a soft boundary on this one. So what we would do, actually, the domain doesn't have any holes or gaps in it, so we wouldn't include that. And it goes to 0, that doesn't have any holes, no holes as well, because 0 is defined, it's just defined at the interval up here, at the closed interval up there. Okay, so we're going to go to 4, where we have a soft boundary, union, and then from 4 to 6, okay, soft boundary, and then from 6 on to infinity. Okay, it's really not that complicated. Now, what would happen, say, if I did this? What would happen, say, if I put in, I fill in this dot right here, I say there's a function value right there. Then I would close this 6 interval, right? And the domain would be negative infinity to 4, union 4 to infinity. Okay, there would no longer be a hole at 6. Hence, that's called these are all discontinuities, and this is called the removable discontinuity. Okay. Now, as far as range goes, that's the domain. As far as the range goes, think of the height, the up and down values that we get out of this function. Well, as I look at it here, it looks like this goes all the way down to negative infinity, and this goes all the way up to positive infinity. And there are no holes in between. Every output value somewhere is taken up in here, so this value exists right there, in case you're tempted to think that that's always empty. So the range would be negative infinity to infinity. Range would be negative infinity to infinity. All right, so there's a couple of cases when domain and range restrictions come into play, and there really are just two, okay? Just two rules that we want to be aware of, okay? Things that you can't do. You can't, and I think of you know, a song. You don't tug on Superman's cape, you don't spit in the wind, and you don't mess around with Jim, right? There are certain things you don't do in mathematics. One, you don't divide by 0. You can't. It's undefined. So let's say I did 5 divide by 0 on my calculator. It would tell me it's undefined, right? But let's say it equals some number a. Okay? We're all aware of this. 12 divided by 3 equals 4. Why? Because that is the same thing as writing 12 equals 4 times 3, right? So the same thing applies here. 5 divided by 0 equals a because 5 equals a times 0. Now think about this. What number could you multiply by 0 to get an answer of 5? And even if you thought maybe it's infinity, if you multiply infinity by nothing, you get nothing. You don't get 5. And so it is undefined. You cannot divide by 0. Not in any number system that I'm aware of, right? You don't divide by 0. Rule number 2, you don't square root a negative. Okay? And we've already dealt with that in the last unit when we talked about complex numbers. In the real number system, you can't square root a negative because you're finding the solution to x squared equals a negative number like negative 4, right? And if x were 2, 2 squared is 4. And if x were negative 2, negative 2 squared is 4. Squaring any number, positive or negative, gives you a positive result. There is no solution in the real number system. Now, mind you, we could say 2i, right? And you're aware of that. But that's the complex number system. So you can't take the square root of a negative. So let's apply that to a problem here. All right? Let's see if I can, well, I'm going to use 2 examples. Okay, first example, let's say f of x equals the square root of x plus 2. Okay, we can't square root a negative, so that implies this. That means that the contents of the square root, okay, the radicand, cannot be negative. So it has to be greater than or equal to 0. Therefore, x must be greater than or equal to negative 2, right? On the number line, here's negative 2. It has to be greater than or equal to, so we fill it in. Set builder notation, we would say all x such that x is greater than or equal to negative 2, okay? And in interval notation, we would say negative 2 with a hard boundary, negative 2, and infinity with a soft boundary. Okay. The second case I want to bring up is this. What if I have f of x equals x plus 2 times x minus 3 divided by x plus 4 times x minus 3. Okay. We cannot divide by 0. Therefore, x plus 4 cannot be 0. And x minus 3 cannot be 0 either. Because either one of those, if those were 0, would result in division by 0. So x cannot be negative 4, and x cannot be 3, right? X cannot be negative 4, and x cannot be negative 3. So the domain excludes these two numbers. So if I have negative 4, it excludes that. 3, 2, 1, 0, 1, 2, 3. So there are holes there and there, right? So I'm just going to do interval notation here. Negative infinity to negative 4, soft boundary, union, negative 4 to 3, union, 3 to infinity. Now, one thing that is worth pointing out is these are not the same, right? So you may note something here. You may notice, well, there's an x minus 3 on top and bottom. Okay, and they cancel out. one of the things that's really important is when you check for domain restrictions, you need to check before canceling, before simplifying. Because even though they cancel out, you cannot cancel 0 divided by 0. Okay, that's a no-no, right? You cannot cancel 0 divided by 0. So when we cancel x minus 3, we add the caveat that x cannot be 3, right? When we cancel. And so yes, this function, f of x, is very much the same as f of x equals x plus 2 over x plus 4. But that's technically not the same function. And it's only the same function if we add the restriction that x does not equal 3. And let me show you what I'm talking about in Desmos. I can demonstrate this pretty well in Desmos. Okay, I'm going to graph y equals x plus 2 divide x plus 4. And I'm going to do y equals, well, first of all, let's do that here. And what happens at 3, let's zoom normal here. What happens at 3 is that we get a value. We get 3, come on, 3 and 0.714, right? All right. But what if I do this? What if I do x plus 2? So y equals x plus 2, x minus 3, divide x plus 4, x minus 3. Right? We get what appears to be the same graph, except for one thing. If I carefully click on 3, we actually get undefined as the output. There is a hole there, and you don't see the hole unless you click on it in Desmos. And so canceling the x minus 3 does not produce the same function. And hence we call that a removable discontinuity. It's a discontinuity, but it's removable. Whereas the discontinuity at negative 4 is removable, is non-removable, x minus 4, because, or x equals 4. Or yeah, x equals negative 4. X equals negative 4. There we go. Right? That is a non-removable asymptotic discontinuity. I cannot simply plug a hole to get rid of it. All right, so hopefully that makes sense. Feel free to book a live lesson.